Hi everyone, I'm Michele, and in this video I will present our paper on generating accurate assert statement for unit test cases using pre-trained transformers. This is a work from Data and AI team in Microsoft. As you probably already know, software testing is expensive. It is estimated that software bugs cost the US economy more than $59 billion annually. More than a third of this cost could be avoided if better software testing was performed. Software testing can be seen as a pyramid, where the foundational basis is represented by unit testing. Here, small pieces of code, such as methods, are tested in isolation. Then, during integration testing, these units are combined and tested together. And finally, the entire application is tested end-to-end. In this work, we focus on unit testing. Here we have an example of a JUnit test case. In the first part, we see that the test case instantiate the class and the environment. This could also be performed in a separate setup method. Next, we see that one or more methods can be invoked. And finally, assert statements are used to check the result, condition, and state of a program. While this test invokes multiple methods, the main method under test is the multiply method. This can be inferred by the name of the test case, which is test multiplication, and also from the fact that some of the assert statements are checking the results returned from the method invocation. We call this method the focal method. In this work, we aim at automatically generating assert statements. The idea is to be able to predict the results, conditions, and state of a program at any point in time, given a partially written test case and the focal method. The idea of generating assert statements was explored previously in this work by Watson et al. On learning meaningful assert statements for unit test cases. Here the authors propose the use of an RNN-based approach to predict asserts. This work also extracts and curates a dataset of assert statements that we reuse in our work. More recently, Mastropaolo et al. Has also applied a transformer models for different tasks, including assert prediction. In our work, we model this problem as a translation task, where the input to the model is the partially written test case with a placeholder instead of the original assert statement, along with the method under test that we call focal method. The model is trained to generate an assert statement for this test case. Compared to previous works, we propose the use of an improved transformer model, pre-trained both on English and source code, which significantly outperforms the previous approaches. We also measure and quantify the impact of this pre-training on the performances of the model. We also show that we can use this trained model to augment EvoSuite test cases with additional assert statements generated by our model. This is an overview of how we train our models. We begin with a BART Transformer model, then we have two pre-training stages with English and source code corpus. Next, the fine-tuning stage trains the model on the assert generation task. At the end of these stages, we obtain 4 different models based on the amount of pre-training we perform. In this figure, the arrows of different colors show which stages are used for each model. Let's take a closer look at each stage. A BART transformer model is a sequence-to-sequence model having 12 transformer blocks in the encoder and decoder, for a total of 400 million parameters. It is trained as a denoising autoencoder. Here are the noising transformations that can be applied to a sentence, such as token masking, deletion, permutation, etc. The sentence is corrupted using this noising transformation and then is fed to the encoder. The entire model is then trained to predict the original sentence without the noise. This denoising task is used during the pre-training stages. The goal of the English pre-training is to learn semantic and statistical properties of the natural language. This is useful because source code can contain a lot of English words, such as variable and function names. Understanding the meaning of these words can be extremely important. For this stage, we use a dataset of 160 GB of English text, extracted from books, Wikipedia, and news articles. The training is performed using the noising transformation we saw before. We rely on a public checkpoint which is trained for 40 epochs. Next, code pretraining. The goal here is to learn the syntax and properties of the source code. For this task, we use a dataset of 25 GB of Java source code, extracted and cleaned from 26,000 repository. This repository belongs to the Code SearchNet dataset. The pretraining is performed for 10 epochs. Finally, during the Assert Finetuning stage, we train the model on the task of generating assert statement given the partially written test case and the focal method. For this training, we use the dataset extracted and curated by Watson et al. In their previous works on assert generation. This stage, the task is not the denoising, but rather the translation task. Here we let each model train observing the validation loss and using early stopping to avoid overfitting. At the end of these stages, we obtain 4 different model variants with different levels of pretraining. BART English plus code with both pretraining, BART code which only has pretrained on code, BART English with only natural language pretraining, and finally BART Scratch with no pretraining and randomly initialized weights. All these model variants have been fine-tuned on the assert generation task, and all the models share exactly the same architecture. We design a large experimental analysis investigating different aspects of our models. First, we compare the performances of our models against previous approaches, Atlas and T5, in terms of top K accuracy on the same shared dataset. In the second research question, we measured the impact of different levels of English and code pretraining to understand whether these stages are actually worth to perform before the fine-tuning. In the third research question, we measured the impact of providing the focal method to our model. The idea is to understand whether we can simply use code completion instead of training our model that takes both test cases and focal method. Next, we investigate the quality of the generated assert, looking at simple and complex assert statements that are generated. Finally, in the last research question, we investigate whether we can use our model for test case augmentation. Here we use our model to augment EvoSuite generated test with additional assert statement and check whether we can obtain code coverage improvements. Let's start with the performances. In this figure, we compare our 4 model variants against Atlas from Watson et al. And T5 from Mastropaolo et al. In terms of top K accuracy on the same test set. Specifically, this graph shows on the y-axis the percentage of predicted assert statement that matches the original assert written by the developer. The x-axis represents the number of predictions from the models generated with Bing search. Here we can see that the BART English plus code model in blue can predict the original assert statement in 62% of the cases in the very first try, which represent the first prediction from Bing search. The model with only English and only code pre-training has slightly lower performances. Our best model, BART English plus code, obtained an 80% relative improvement over the previous RNN-based approach Atlas, which is represented in red in this figure, and 33% relative improvement over the T5 model, represented in black. Here we can also see that our model with no pre-training, BART Scratch, is slightly worse than the T5 model by Mastropaolo et al. The graphs for Atlas and T5 appears like a step function because their paper report only the results for specific top K value, while we report the results for any K value from 1 to 50. In the second research question, we want to understand the impact of the pre-training. In the previous slide, we already saw that in terms of top K accuracy, the model with both pre-training slightly outperformed the other 2 models with only 1 pre-training, and significantly outperformed the model with 0 pre-training. Here we analyze also the validation loss and other intrinsic metrics. The figure shows the validation loss during Assert Finetuning. Here, of course, the lower the better. We see that the pretraining allows for better initial and final validation loss with faster convergence. Again, the best one is the BART English plus code in blue with both pretraining, while we notice that there is a large loss for the BART Scratch, here depicted with an orange line, which has randomly initialized weight and no pretraining. In terms of intrinsic metrics, we measure the blue score and the syntax correctness of the assert statement generated by the model, analyzed with a Java parser a different number of predictions. We see again that the BART English plus code has the best blue score and top 1 syntax correctness, while the BART code has slightly better syntax correctness for different top k values, which makes sense. Overall, we observe a noticeable improvement with either English or code pretraining, with the best performances that are achieved when both pretraining are combined together. In the third research question, we are trying to understand the impact of providing the focal method to our model during training. The basic idea is that if providing the focal method does not improve the performances, instead of training our model with both test case and focal method, we could simply use a code completion model that predicts the next statement. In our case, will be an assert statement. The figure here shows the top k accuracy for the models with and without the focal method. The solid line represents the performances of our best model, BART English plus code. The dashed line instead represents the model with the same level of pretraining, but fine-tuned without the focal method. We can see that the focal method allows for 10% better performances in top k accuracy. This means that a generic code completion model will not outperform this model, and that the focal method provides essential information for the model. Here we manually analyze the quality of the generated assert among the perfect prediction that matches the original assert statement. We found that the model can generate common assert statements which are often found in many test cases. For example, comparing an expected variable with a result variable, that the list contains the element that was added, or checking that the size of the result is equal to 1. Additionally, we also found complex assert statements among the perfect predictions, which involves multiple method invocations, complex parameters and values. Additionally, we also analyzed predictions that do not match the original assert statement. We found that the model often generates equivalent asserts to the ones that are written by the developer. Here in the first example, we see that the model suggests to get the class literal directly with the abstract service.class, while the developer used the method getClass, which in turn used the same class literal. The next one, the developer checks the equality returns true, while the model uses the equivalent specific assert equals for the same check. It is worth noting that these equivalent asserts are not counted in the previous research question in terms of performances. Finally, in the last research question, we investigate whether we can use our model to augment EvoSuite generated test cases with additional assert statements. The basic idea is shown in this figure. We first ask EvoSuite to generate a test case for a method. Then we use this test case as input to our trained model along with the focal method. Our model will generate one or multiple assert statements, which are then added within the EvoSuite test cases to obtain an augmented test case. The intuition here is to obtain a test case that performs additional checks on the results, behavior, or state of a program. We evaluate this idea on a small testbed offered by Defects4J, which allows us to easily replicate these results. We start by selecting 18 focal methods from lang1f. Then we let EvoSuite generate test cases for 500 seconds, around 8 minutes, and compute test coverage using defects for J built-in tool Cobertura. We compute the test coverage for each individual test case, and we can see the details of this in the first 3 columns of this table. Next, we perform inference with our model, passing as input the test case generated by EvoSuite and the focal method. As output, we obtain an assert statement that we inject within the EvoSuite test case and compute code coverage again with the augmented test case. The table shows the details of the code coverage improvements in terms of line and condition covered. First, we see that our model is able to generate asserts for all the methods except one. In the last 2 columns, we also see the code coverage improvements with the additional assert. We see that in most cases the assert can increase the code coverage by 1 line and 1 condition, and in some cases even 3 additional lines and branches. However, there are cases where no improvements are seen. Overall, these preliminary results suggest that this approach could be helpful in augmenting automatically generated test cases with additional assert statement in order to improve coverage. However, of course, larger studies are needed to confirm these results, and additional metrics should be considered, such as mutation score. To conclude, here are some examples of what the model is able to suggest. In this first example, the test case has 2 for loops where it inserts some values. Then, in the last for loop, we ask the model to generate an assert statement for this exist focal method. The model generates an assert that considers the literal number 100 and the loop variable I. In this second example, the partial test case creates an event object with an event factory, and the model is asked to generate an assert statement for the create method. The generated assert correctly checks that the event object is an instance of the correct type. In conclusion, we propose an approach to generate accurate assert statement using pretrained transformers. We show that our model is able to outperform previous approaches based on RNN and T5 models. We also measured the impact of pretraining, demonstrating that both English and code pretraining provide benefits to the assert generation task. Finally, we show that our model can be used to improve and augment existing test cases generated with test generation tools such as EvoSuite, in order to increase code coverage. You can find additional information in our paper, and thanks for your attention.